Okay, well, listen, thank you very much, Tim, and good evening, I guess, for most people on the call. I suppose it's all the London chapter, so I'm assuming it's evening for most over there. As you can hear probably that I hail from those shores as well, although I'm currently based in Houston. And as Tim had mentioned, I do originate from an engineering background, specifically mechanical engineer, but I'm hoping that during this talk and this presentation, I will spur a bit of interest to the mechanical engineers, maybe a little from the electrical engineers, but more chiefly, my main audience really, or main group of people that I hope is interested by this topic are the petroleum engineers, perhaps more rare beast right now, considering the changes in the industry, and all of the all of the changes in the industry. Let me leave it at that. But what we have here, what I'd like to address here today, is some of the efforts on what is perhaps the new word of the day, electrification, if I may. It's a big word, but there is some reason and resonance behind it. And I hope that from this presentation, you'll get a bit of an appreciation of where we started as Schlumberger, myself as well included in that journey over the last 10 years of really starting to bring some of this transition into bear for, again, the same people, the petroleum engineers who actually have the hard job today of sustaining recovery, being a relevant part of the industry to make energy for future generations, but to do it sustainably or as sustainably as possible. Because after all, at the end of the day, whatever happens with the transition, we still will have an energy creation industry from hydrocarbons for some decades to come. So sustainable recovery with this decade of reach contact and intuitive control. I hope by the end of this presentation, you'll get an impression that really we are talking about a bit more intuition in the control of our reserves, our subsurface reserves. So the agenda for this talk, it starts out with the electrification, a Schlumberger perspective or a major service co perspective. There are multiple parties engaged on this transition in technologies for the energy industry. I'll spend a bit of time on our approach and some of the architectural decisions that we have taken, and hopefully for the mechanical and electrical engineers and completion engineers, hopefully this will resonate with those folks, and of course a little bit on the track record that we have generated over the last 7 to 10 years. Then I'll take a little bit of a futuristic view and look at what could be done with this, with this capability, and bring together a couple of examples. A few of them have been, or at least one of them has been published multiple times. So I'll try to utilize and dig into case history example there. And then I'll finalize with so what next and why now? I think those are the key questions that we're being asked as completion engineers, and particularly in the intelligent completions domain, which is where this whole electrification story really started for the subsurface part of the industry. And then as a little bit of fun, I hope to be able to address the question on the right-hand side there is what really relates these two images. And I thought I'd make it relevant with a London bus. Apparently that's the new London bus. And I have some interesting fact there, which I'd like to leave you with at the end of this, which is relevant to the electrification story. So Schlumberger is by its very nature, it started as a company, in the early 1900s, really around electrical principles. So if you think electrical, then of course, Schlumberger is part of our makeup, part of our bread and butter. Even though I'm a mechanical engineer, I came in and of course was met with 3 electrical engineers for every 1 mechanical engineer back when I joined. But the approach that Schlumberger is taking for the electrification is really a system approach. So what you see on this view graph here is a rather illustrative version of a subsea type of an application where you have, an extended, an existing field extended in the background there, the back right of the view graph, that may be maturing and is already producing, and then a satellite field in the foreground, which is, of course, associated with potentially subsea satellite type of development. So when you talk about these things, really where we've started and where our growth from the subsurface began is in the bottom right, which is surrounding a tool or a technology that we have named Manara. and I'll spend a bit of time on this, but it is essentially an electrical flow control valve with some downhole monitoring, really focused on the reservoir. And I think that's a great place to start, because it really is the birth of some of the other systems that you can see that are currently either under development or under the roadmap with respect to the system approach. So you'll see here some downhole surveillance capabilities through fiber optics with downhole connectivity capabilities. Inductive coupling I will touch on during this, because it is a fundamental piece of the electrical subsurface architecture. Some downhole and sand face type of completions for those of you dealing with solids producing or solids prone reservoirs. Those become more important, especially in offshore environments where you need to have longevity in terms of the completion performance. But then as we move closer to the subsea and the surface, of course, there's a lot of interface capabilities that are needed as part of this electrical system. Oh, I missed out one key component, which is for every offshore well, at least, there is generally a safety valve, and therefore electrification would not be complete if there were not some programs of effort on electrifying or allowing the safety valve to be driven electrically. But with regard to the interfaces, this is really an area of fundamental focus, and you will probably get to this during this talk. But it's a really fundamental key component of the overall electrification for all of the subsurface to function effectively. Clearly, it needs to get electrical power and communications through the interface. So things like the feed-through systems, both optics and electric, are very important. And then also all the way back through actuation at the manifolds, or whether you're on boosting stations or on the tree itself, and then back, of course, into platform, where, of course, surface electrical actuators are also quite common these days. Conversion from hydraulics to electrics is not uncommon offshore, even to the point where offshore facilities start to become powered from shore, notably on the eastern side of the North Sea there. A lot of effort and a lot of desire on electrifying the platform, existing platforms and or new platforms, to make it more efficient use in terms of extraction footprint. So Schlumberger has been looking at it more from a systematic approach, from, let's say, from the pore space or from the reservoir itself all the way to the top sides. Not all of these technologies are going to come out at the same time. Most of them are on their way. Some of them are already commercial and already have track record, and I'll show a few of them for the subsurface. But all of them are part of a multiple company, multiple operator interest in the industry. And therefore, there are different pieces of these being relatively developed, either alone or in partnership with different operators, in order to bring this as a system, this capability, to the industry in the next couple of years or so, plus minus, to really leverage that opportunity to extract the resources that we all know is there, but could be somewhat stranded at the current rate of returns expected from the investment dollar. So a couple of the key drivers, if I go back to a couple of the key drivers with this new fashionable phrase, electrification, or subsea electrification, maybe more specific, but a couple of the key drivers there are clearly the reduced footprint. And I don't know if you have seen or read the literature, but there is a lot of interest in satellite tiebacks. Of course, it's nothing new. Satellite tiebacks, nothing new, but extending those tiebacks to existing facilities and continuing to reutilize or even refurbish and reutilize existing fields, production stations, which may be dropping off in terms of their load from the production from their existing fields, and being able to tie into those and produce from new greenfields or extended from the existing field is really an important driver, of course, in reducing capex, but also in reducing the carbon footprint of that development or that extra barrel of oil produced. Power from shore, I mentioned in the context of the platform and surface type of facilities. Clearly, this is a key desire in those locations where it is possible to transit power from shore, which is more from potentially renewable sources, like in the Norwegian sector and the the hydropower generated electricity for power from shore activities. But the extended tieback is really the goal. Getting those access to those resources in a cost-effective, low-footprint manner so that there is a more responsible and more sustainable recovery of those existing reserves, which are known to be there, but may be striving to extract the capex dollar based upon the financial challenges associated with the development in these type of high-cost environments. Now, from a Schlumberger perspective, we also have to look at the downhole piece. So when you talk about Schlumberger and at least the historic portion of the subsurface, so I come from wells and well testing, so everything to do with the reservoir. So of course it starts really with the subsurface from our perspective. And when we talk about electrification and some of the drivers for downhole and subsurface applications, well, they kind of start with the utilization and efficiency of the surface footprint, whether that be on land, quite frankly, or in this case, illustrated offshore, where there may be limited numbers of slots available to drain a certain acreage of reservoir, and or slot recovery, so the ability to go back into existing fixed platform type of facilities and well bores, and then target unrecovered oil pockets at maybe the flanks of the field or between existing producers. So this is where electrical capabilities and the flexibility electrically powered downhole devices brings is in some of these domains on slot utilization and slot recovery. But also, if we go further into the reservoir, whatever we can do to increase the contact, assuming that the reservoir has the ability or has the extent that increased contact is going to make a material difference. But wherever we can increase the contact, of course, the additional barrel per foot of increased contact is going to give you additional barrels, but you're going to be trading that off versus the cost, complexity, and risk associated with drilling and completing that extra foot. At some point, there's going to be a balance in terms of where the economics and the return on that investment makes sense. Now, the benefit of electrics is that you have the possibility today to increase the contact. And today we are completing wells with over 3 kilometers of horizontal section offshore, shallow type of application, shallow field type of applications, with up to and even increased above 6 zones, although typically we're completing 6 zones with these electrical devices. So if you're from the basins of the world, offshore basins, typically subsea, where you may have multiple zones or multiple horizons that you would like to complete as a petroleum engineer in order to recover those reserves. Currently today, you're kind of limited to a couple, typically 2 zones if you want to do these things intervention free. So the ability to be able to increase the number of zones and also the increase the contact as well puts the acreage of effort downhole below the surface, and of course enables you to have multiple drain points. The other key factor driving or at least where electrical downhole completion devices have been enabling is on extending the reach. And today in some applications, we're actually able with the operators to be able to drill and complete, again, 6 zone type of completions at extents of measured depths of 14 kilometers plus. That's an extended amount of step out. Could be from a false island type of approach, or from an island to a sort of a near shore type of field. But extending those drains out to 14, 15 kilometers, potentially adds significant return on investment potential with limited slot space from a platform or from a drill site. A couple of reference papers with regard to what we present today. I'm going to refer down the bottom left. You'll see the little SPE reference comes up there. But in reference to this particular aspect, if we look at the electrification perspective as well, when we talk about slot utilization, recovery, increased contact, and extended reach, what we really mean is cash at the end of the day, and recovery or additional barrels. So particularly in water flood type of environments, where you would instead of controlling your production at the wellhead, you have the possibility to control at multiple zones from the reservoir, right at the reservoir itself, can lead you to a proactive or even, sorry, a reactive or even a proactive management method, drainage management method with water flooding, where you can use the reservoir model to actually proactively position the production or allocate the production per zone and therefore drain more effectively. And what you see here is the probability curves for the flooding efficiency increase as you go to more of a proactive approach with more zones controlled and more visibility. What does this ultimately mean? Well, it ultimately means more zones with potentially less wells, depending on the drain you have and the production risk that you associate with each of the well bores. Potentially less wells, so therefore less potential capex, but definitively more barrels. And what you see here is another highlighted, typical recovery curve for which compares base case type of recovery with no control to the ability to access those additional zones, so additional 2-3 zones of production, and then finally to be able to control those zones so that you're able to adjust for water entry or gas entry. And typically, you're looking at conservative gains of 20-30% incremental recovery at least, and simulated timelines of 10 plus years. So significant additional gain to be had, and ultimately less OPEX. So what does less OPEX mean financially? It means it's good from an operational standpoint, but also there is less lifting footprint, so less CO2 cost per barrel produced. And I think, when you look at the ability to extract more from existing facilities, clearly CapEx is one of the domains, but also the footprint of draining those extra barrels more responsibly becomes more and more important as time progresses. So what is our approach? So as I mentioned at the beginning, Schlumberger's approach, it starts with the subsurface. I'm in wells, so naturally it starts with the subsurface from our perspective. So if we take that sort of reservoir that was in the distant, which has got, maybe potentially heterogeneous streaks, could be a turbidite, could be a channel sand with relatively, non-uniform type of plays. Could also be an oil rim where it's important that you understand where, for instance, gas cusping or water coning or channeling or viscous fingering events are identified and managed. Then the ability to split that producing horizon into different producing units or compartments, let's call them, or zones. I'm going to call them zones from now on, but zones could mean compartments within the same reservoir interval, but the ability to do that can afford significant gain with respect to managing uncertainty in production and ultimately, of course, offsetting for production uncertainty from the reservoir itself. So what I'm illustrating here is a 5-zone type of application, just to give you an illustration of the type of things that we can do. So when we look at it from a jewelry, so I'm taking the mechanical engineer approach right now, when we look at it from a jewelry piece of perspective, and we look at this 5 intervals or 5 compartments to complete, typically we may complete them open hole, or we may install some form of sand control device. What I'm illustrating here in orange is a standalone screen type of an application with multiple open hole packers. Those open hole packers could be swell, they could be mechanical, depends on, could be expandable type of packer. So I won't go into detail into each of the technologies, but what you can do is you can preserve or at least stabilize the formation with different types of sand control technique as a first step. And what's illustrated here is a typical 8.5-inch open hole, or it could be a 6 1/8-inch open hole. But in this case, if you run the screens, you could run 6 5/8 or 7-inch standalone screens inside an 8.5-inch open hole. And you can provide the open hole isolation between those intervals, between those producing horizons. So then what we'll do is we'll typically deploy a series of control points. So these blue blobs that you see here that I'm illustrating with good old PowerPoint simplicity, these are supposed to represent electrically driven flow control devices which will allow you to selectively produce from each of these horizons. In between each of these inner string type of flow control devices, you have a packer. So you have a packer sealing within, in this case, within the open hole packer that's sealing to the open hole. So you basically are compartmentalizing between each of these 5 drain holes, and you're compartmentalizing with an electric flow control valve, an EFCV. Now, Schlumberger's name for the first EFCV that we started deploying, 9 years ago, 2012, is called Manara. That's not so important. What is important is that it is electrically driven and it does have onboard surveillance. Another key component is the fact that it is work string deployable. So what that means is you can deploy this inner completion string on drill pipe, and what connects that drill pipe to that lower completion is part of an inductive coupler, which I'll come to in a couple of slides. But the fundamental purpose here is enabling us to be able to deliver multiple control devices. It could be 2, 3, 4. In this case, illustrated here is 5, and we've deployed 6 of them in line in multiple cases now. Allows you to deploy them on drill pipe. So you've got the security and the simplicity of deploying on drill pipe. What that allows you to do then is, once that's deployed, now you've set all your packers, you've got everything landed, and your electrical completion is now landed in hole. You come out with your drill pipe and work string, and then you run in hole with your upper completion, and you land and space out and land, I should say, excuse me, the inductive coupler between the upper and the lower completion. So what that allows you to do is it allows you to pass power and communications electrically from the upper completion, where my mouse is, to the lower completion and back. So what that is a permanent electrically enabled powered completion that allows you now to be able to visualize what's happening from each of these producing compartments and be able to react to it with the electric control. And I'll show a couple of view graphs of that in a second. So how does this Manara, or this EFCV, what does it look like? So this is the first electrically driven flow control device deployed with the full monitoring capability in early 2010s. And what it looks like in cross section here, you'll see here, is it has a screen interval, which in this case is a debris barrier. So if you can imagine the flow from each of those zones that is compartmentalized here is coming in through this barrier, through this screen barrier here. That flow is passed through this side pocket type of style of flow path. So if you want, that's actually a 1-inch tube sitting on the side of a 3.5-inch pipe, essentially. And what that allows it to do is it allows that flow to get passed through this side pocket. It is metered through this Venturi device. And then before it joins the main production flow through the 3.5-inch tubing, before it joins at this point here that I'm highlighting with my mouse, you have this control point. And this control point is nothing more than a electrically actuated plunger device, of course, highly designed, high erosion resistant, carbide materials, etc., which allows one to be able to meter that production from that particular zone. So each one of these blue illustrated stations here will contain its own metering section, which I'll come to in a second, and its own flow control device, electrically actuated. The electrical actuation is provided by a DC brushless motor encased in here. There's a gearbox in here as well, and basically it's all enclosed actually in a metal welded enclosed bellows, in fact. So there is absolutely no contact with reservoir fluid, allowing this motor actuator to not be affected by reservoir fluids. And this rod here that you see in blue is actually actuating this plunger device, which, as I said earlier, is placed here in the station. And this is what actually does the metering or flow choking or control, if you will, flow control from each of those zones. That's where the flow comes in through this flow path and is metered into the production stream. So the advantage of having this electrical actuator is, number one, is that you can move this with an infinitesimally small resolution. So because you have multiple positions you can place it in, but it's essentially infinite. We have elected to set our control system at 100 positions from fully open to fully closed, but essentially it's the resolution of 1 turn of the motor, which is much less than 1%. So you have the ability to infinitesimally small adjust this choke. So if your analog could be the thermostat at home, where you chip it in, you increase it by 0.5 degree or 1 degree because it's winter time, and my spouse will then come and drop it by 1 degree or something because she has a different threshold. You can do the same with this electrical device because it allows you to be able to meter not only closed, but also open. And one of the challenges that we have with hydraulic systems is that to do the same thing, typically you have to go through a mechanical device. And what that typically means is you have to step through an indexer type of arrangement. If you want to choke back a zone, typically you will need to step a hydraulic control valve through the next open positions, so multiple open positions all the way to fully open, and then to close, and then to step it through the next step. So what that means is it means a hindrance to the petroleum engineer in terms of operating those zones efficiently, because if you make a mistake on adjusting your individual zone, you would then have to go through a fully open and a fully closed position, which may be disruptive to the production scenario. So electrical removes all of that, because if you make a mistake, you just adjust it back. You say, okay, I'm going to take off that 0.5 degrees C that I decided to add on to my thermostat at home. I'm going to put it down by 0.5 degrees C. I do not have to put it up to 100 degrees C and then 0 degrees C in order to be able to get that step. So very important component, I think, is the confidence of the petroleum engineers to utilize these tools. And that's something I hope I will get across during this talk today. Now, as I mentioned a little bit already, that on board this system, we also have a series of surveillance devices. And what I've highlighted here in red, these red bullet points here, you can see, are 3 things essentially. The first on the left-hand side, which is downstream of this venturi, so the flow comes through here, is mixed. But what you see here is a water cut probe. This is an early picture of one of the prototypes, but this is what it looks like. This probe is inserted into the flow stream downstream of the venturi. And what that does is it measures electrically, specifically capacitance. It measures the capacitance of the fluid flowing past or through this tube here. So when you have water coming in an oil producing environment, of course, you've got a conductive fluid that will then be detected by this capacitance probe and quantified by that capacitance probe. So we're able to quantify the amount of water produced in an oil producing interval. And then you have this venturi itself with 2 pressure measurements, one here, which is upstream of the venturi, and one which is at the venturi throat. For those of you who've been familiar with the multi-phase metering or multi-phase meters, is a very common device, is to have a venturi flow meter. So what this allows you to do is it gets you your upstream pressure, which is essentially your zone producing pressure. So that's the, as your zone is producing into your wellbore, that's PWF, some people would call it, the downhole flowing pressure at the reservoir face for that zone. And then on the throat is the throat pressure. And when you combine those two, you get the mass flow rate of what's being passed through this venturi. So if you have the mass flow rate and you have the densities of your different fluids, and you know the water cut from this probe here, you've got your 2-phase flow rates. You've got your water and oil producing rate, oil and water flow rate. In addition to that is the valve position. So we pull this from the motor itself. We have a resolver on the motor, which pulls the position accurately of the position of this plunger. So you always know exactly which position you are in, even if you have a shutdown on the platform or your power supply is tripped for whatever. That same information is stored in the downhole tool's memory, and it stops as is, so it doesn't move to any particular position if the power goes out. So when the power comes back on again, it knows already, okay, I was in position 30% closed, and it starts from there, and it knows exactly where to go. So it's got all of the onboard capabilities to restart in the case of a contingency situation. I will play this animation here just for the purposes of hopefully illustrating it. I won't spend any time on it, but you will have the recording, and of course I can refer you to these animations if it's of interest. But this is actually an open hole illustration, so deployed in open hole. There you can see the water and oil flowing through this sort of sand screen filter. And here is the flow of fluid coming through the venturi. You have your upstream pressure here and your throat pressure measured here, which is now giving you your mass flow rate. And then downstream of that, you've got your mixing that is created by the venturi itself. Oil and water is nicely mixed downstream of this. And the water cut is extracted from the capacitance measurement in this probe here. And then the flow is metered through this flow control device, which you'll see close in a second. And it's metered directly at the point of entry into the main bore. So what that allows you to do here is it allows you to have the visibility on each of the producing horizons and the control, almost as if you had one well with a choke at surface and a bunch of monitoring suites at surface, you know, a multi-phase meter on your production line. But now you're passing that capability downhole, and you're able to multi-drop those devices all on a single cable. So that brings me to the next piece of the architecture and the approach, which is really the cable. So the cabling is it's very simple. It's a mechanical device at the end of the day. It's materials, etc. Right? What we actually utilize is a twisted pair conductor. This is very important for anybody involved in specifying trees and facilities for, you know, future developments. Twisted pair actually means you have two conductors inside of a 1/4 inch control tube. So where my mouse is showing the red two conductors inside a 1/4 inch welded tube. Essentially, it's a 1/4 inch control line. We call this a PDC, permanent downhole cable. So these twisted pairs are, in order to be able to pass power and communication, we actually use an AC, alternating current downhole, in order to be able to do that. And I'll come to that in a second. But all we have here is to be able to provide the power and communications bidirectional from the downhole devices to the surface and back again. What I'm illustrating here on the right-hand side is for some of the applications where, especially where there are ERD applications or even multilateral applications, where we actually pass these stations out through a junction or through convoluted types of well paths, then protecting this cable is important, because clearly that's where the power and the communications is from. If you break the cable, you don't have power and communications anymore. So what we actually have is what we call bumper bar protected PDC. And what that means is you have a 3/8 inch bit of wire rope either side of the cable itself, the electrical conductor cable itself. And that is further encapsulated by this plastic encapsulation, polymer encapsulation. These are highly robust cables that are really only needed when you have very difficult well bores to enter into, or long trajectories where you have concern about this cable. But these have been used, as I said, in multilateral type of applications, going out through, you know, cut windows in the side wall of a liner, etc., and to a lot of high degree of success. So this is the backbone. Let's call it the backbone of the wellbore. And the connection device, as I mentioned before, this green piece here, which is actually two pieces, is provided by what we call an inductive coupler. So what that is consisting of two pieces. So you have a female inductive coupler, which is usually run as part of the lower completion. So that's what's sitting up at the top of the lower completion. And we have a male inductive coupler, which is passed in and spaced out to land inside of this female. When those male and female inductive couplers are mated, you are able to efficiently pass electrical power and communications from the upper completion out into this male and then down into the lower completion. And that is where we get our connection device. Now, what's really important to note here is the fact that these male and female coils that I've zoomed in here, these are actually the power and communication coils that are encased within the female. And in fact, the same is on the male side. But what's really important here is that these are encased with a metal enclosed sleeve on both sides. So what does that mean? It means that the male coupler is fully metal encased. It's an inconel encased. It's like a piece of steel, or a piece of inconel steel, I should say. And then the female, the same thing. It has this metal inconel encasement. What does that mean? It means that my male and female are fully metal enclosed. They have an electromagnetic coil inside of each, but there is no contact between the electrical wires inside of those coils and any of the downhole reservoir fluids. And what that brings is it brings a high degree of robustness and reliability between the electrical communication between these two connections, because essentially it's akin to your recharging toothbrush that you put next to your sink, in the bathroom overnight to recharge. You do not expect that to short out, right? It is fully sealed, in that case, in plastic. What we're sealing it with is inconel sleeves, so you have something which is H2S proof, obviously oil and water and acid proof, so allowing you to make a reliable downhole electrical connection. And the animation here just illustrates a bit better. What you're looking at here is where my mouse is actually an open hole packer. This is an open hole packer as part of a lower completion. What you're seeing passing through that packer is the electrical cable that goes through that packer. And then what you see here animated is the female inductive coupler. Actually, sorry, it's here where my mouse is pointing. Right here is the female inductive coupler sitting up inside the liner in this case. And what you see on the left-hand side coming into place and that will mate is the male inductive coupler, and then a packer at the top, which will be your production packer, which is obviously a main seal in the well. And you can see that you come down as you're landing that tubing hanger, these would be spaced out so that you end up with this male and female connected and aligned. And you can see the coils inside there illustrated quite nicely. So now you have power and communications going through from male to female into the between the upper and lower completion. So what does that allow? That allows a degree of flexibility, but what's really, a degree of flexibility with deployment of these electrical devices, and any electrical device that can be powered with an AC power source. But what's really important when we talk about electrification is the reliability and the robustness. So what Schlumberger, what we're focused on is, of course, reliability and robustness, and we're really focusing on the backbone of the system. So what is the backbone of the system? So what we showed was the electrical flow control valves and the inductive coupler being fully enclosed, metal enclosed devices, no contact with the reservoir fluids, or no contact of electrics with the reservoir fluids. The same goes with the umbilical and the electrical cabling. So what you have from surface is essentially you have a tree power supply. I'll come to the actual power levels in a minute, but this is going to supply an interface card. This interface card is typically deployed either in an acquisition box at surface if you're on a platform, or it's in a canister or in the subsea control module sitting in the tree on the subsea tree on the subsea bed. And then this is then converting the power supply provided by the tree to an AC signal going downhole through a twisted pair cable. And this is what I mentioned before, twisted pair cable is then passing through the tree itself. So you have here the penetrations through the tree. This is actually a dual contact, two contact single pin connector, which goes through the hanger of the tree for those on the subsea side who are interested with it. And then passes downhole through a series of potentially dry mate splice connectors. Typically, you're going to need to make a connection on the cable at some point. So it's a very important part of the puzzle and the robustness of the system is to make sure that this is fully enclosed, fully sealed, fully metal enclosed. And then comes down through this illustration of what the inductive coupler looks like in its gut form, its electrical engineering form. So you have a power and a communication coil, which is enabling a transition from your upper completion power and communication across the jump into the female, and then into the lower completion twisted pair, which is illustrated here. And you can see how the signal propagates. You have the power on a major AC frequency, and then you can see on top of that these little spikes. That is the communication that is going on top of that power signal. And then the flow control device or the monitoring devices are connected in parallel to this bus, this main bus. And what you'll do is that power signal will be converted to typically a DC voltage to power up the electronics downhole, go through a telemetry and power management series of electronics, and then we'll go into the guts of the tool, either the motor, if you're controlling a motor like the flow control valve, or if you're controlling some sensors, you go through a sensor control board as well. So all of these things are on parallel. They come off of the bus. And what's critical here, at least from a reliability standpoint, is that what Schlumberger has taken as an approach is really to build the backbone with absolutely no in-series hybrid electronics. So between the subsea interface card and the AC to DC modules, the rectifier circuits in these electrical devices downhole, there is no electronics in series. It's all coils and wire. That's all it is, essentially. So you've got the most robust that we can design from a backbone downhole, such that if you have a challenge with the subsea interface card, okay, at least the subsea interface card is removable. But what we're trying to do is avoid any need for any breakdown of electronics that can affect the full system that goes in series. So this is really our approach that we have designated, and I wanted to highlight to those of you who may be involved in specifying subsea facilities, that what this means is when you hear of AC downhole systems, what we mean is alternating current downhole. However, from the tree itself, we are not yet requiring any alternating current from the tree. We still require, this actually happens to be 24 volt, 96 watts DC. This is still considered sufficient for most applications of downhole electrical flow control valves. And this is then the conversion for the AC is done at the subsea interface card. So simplicity at the subsea tree level is still an IWIS 1, 2, or 3 level power supply. This specific example here is typically what we're looking at, about 96 watts DC maximum for this type of an arrangement of number of zones, etc. So what does this allow? So the first thing it allows is a degree of flexibility in well architectures, and I'll breeze through these very quickly. Please do not worry about it. If it hopefully it's going to make sense, but do not worry about it from a detail perspective. What I'm trying to portray here is that you have a degree of flexibility afforded by electrical completion devices, which is not available with typical hydraulic completions, or is very complex to deploy. The first is multi-zone, or multi-zone with an ESP. So here you see a single stage, 3-zone. It could be a 6-zone completion, but a three zone single stage completion where you're running from dry tree or wet tree application, doesn't matter. And then you have a 2-trip application here with the same number of zones. Just for illustration purposes, I placed an ESP there. We have run ESPs with 2-trip intelligent wells. And what you have is this inductive coupler connecting the upper and lower completion. So it allows you to remove the ESP if you need to replace it, and rerun the ESP with this male inductive coupler placed on the bottom, so you can mate up the upper and lower completion and provide power and communication back to the downhole devices. So very flexible completion, fairly simple and quite well utilized. We have extended reach, a lot of experience. Almost 70% of the wells that we have, or zones, almost 70% of the zones that we've completed with these electrical systems are in extended reach applications. And the example here is a 6-zone, or the maximum that we have done so far is 6 zones deployed at 14 kilometers measured depth. That's the total measured depth of the well, with almost 3 kilometers between the TD of the well and the uppermost point of the reservoir contact. So between the six different zones, almost 10,000 feet of contact that is deployed. And a lot of capability that affords is the ability to deploy, but also the ability to manage those resources without intervention. which of course in extended reach would be challenging. And then what's becoming more and more interest today is multilateral. Multilaterals have been around for many, many years, but what's becoming more obvious today is the ability to utilize this for more effectively using, your slot utility, either well drill site on a subsea bed, or even at the platform level. And we've deployed these type of systems, electrical systems, where we have the ability to control a zone in the mother bore, and then control the lateral zone at the junction, so that this is actually a zone controlled at the junction. So we're actually controlling the production at the junction here. And we've also added in what we call a side lateral entry sub. So there is the ability with this side lateral entry sub to be able to, if needed, to be able to intervene with an intervention tool into that side lateral and to intervene into here. In this particular case, this particular example, they had a drop-off liner with ICDs in this lateral that was being used to control inflow, and then controlling the junction with this electrical flow control device, allowing some flexibility there on production. And then, at the time anyway, in 2015, when this well was deployed, which was actually a full multilateral with what we call in-lateral control, which was actually a trilateral well with 2 zones or 2 compartments deployed in each of those open hole lateral intervals. They were all a level 3 lateral for those who are interested in. So not hydraulically sealed at the junction, but mechanically covered, right, by a sort of a drop-off or a tieback liner in each of the laterals. What that allowed to do is to increase the contact of this reservoir or this wellbore with the reservoir to a total of 10,000 feet per lateral. So in actual fact, we had 30,000 feet almost, or 9 kilometers of contact of reservoir split between 6 producing intervals, controlled producing intervals, all tied back through an electrical system which utilized the liner itself. So we actually cemented a liner with the inductive couplers as part of the liner. And if you want, that became then the electrical plug-in points for each of those lateral completions, which allowed us to be able to multi-drop from the upper completion power through this inductive coupling system out to the liner, in through this inductive coupler, which then powered this wellbore. And then likewise, you can do the same through this second and third inductive couplers to be able to power and control each of these laterals. So enabling quite a lot of contact and recovery enabled from a single wellbore or drill site. And this particular one was actually on land in this particular instance. So reliability. So electrical systems, the obvious question is reliability. It does not come easy, and I won't spend much time on this, but what I wanted to highlight is that from a Schlumberger perspective, 1972 is a key date because that was the first permanent sensor deployed back in the day. Since then, we have over 15,000 pressure temperature sensors deployed. So that's our electronics, downhole electronics experience. And they've gone through a number of, let's say, technology evolutions. Initially, utilized through-hole PCB electronics. And you can see here on the right-hand side, the reliability or survivability plot during that phase of what we call the PQGs back in the day, back in the 1990s, that were deployed quite extensively, actually, across the offshore applications. And you can see here around about 80–85% type of survivability over a 10 to 20 year type of time frame. However, over the generations, one of the things that has evolved is the downhole electronics to multi-chip modules. So the first generation here illustrated in orange showed a marked improvement in the survivability, but also we focused on dry mate connectors and utilizing dual redundant seals to enable that backbone to be as reliable as possible. So this one enabled a jump in survivability and reliability, as you can see between that gray and that orange curve here on the population of gauges that was installed. And then the second generation of MCM technologies, where we removed much more of the organic components. We started sealing the MCMs themselves and providing dyes that were installed as part of that multi-chip module, basically in an effort to remove anything to do with organics in those electronic sections. allowed us to move that reliability or survivability curve up a notch again. So in terms of reliability and robustness, it's becoming much more representative of what could be accepted for a downhole flow control application. And then the most recent, a change or an increase in the temperature rating of those downhole electronics, now utilizing the sun high temperature technologies, which take that MCM technology to the next level. And we've introduced a triple actually shaped memory alloy type of seals for the dry mate connectors as well, to further enhance the connectivity and the robustness of the backbone. So none of this is possible without a deep and extensive ecosystem for electronics. And what you're seeing here is some part of the qualification process on downhole electronics. That's a downhole electronic device being powered and undergoing hot shock. So it's under temperature in an oven, but it's also being shocked. And you see here an example of the sun technology MCMs, which are microchip modules. But what you see here is encased in this enclosed, let's say that where the atmosphere is controlled, enclosed in here, in this cap, is all of the electronics which are used to to control the sensor and or the motor themselves. And then another key component which is enabling for the deployment of these electrical systems is what we call the data acquisition and transmission system, or the downhole interface, effectively, in the simplest word. And this is an example where what we've actually been looking at is trying to add on the capability of system diagnostics to what ultimately needs to manage the power and the data acquisition and transmission for downhole. This system diagnostics piece is, we believe, something critical for the electrification of the subsurface to work, because what that allows one to do is allows an automated backbone verification of the electrical system itself as you land the tree, as you start up production, as you clean up, etc. So at least you've got some visibility of how well that's going. And you can do things like time domain reflectometry, which is part of the electrical tests you can do on the backbone. Also, you have some basic oscilloscope capabilities, which allow the electrical engineer to actually poll the electrical signals which are coming from the well itself and do it over time. So it allows you to do this in line during production phase, which will help on at least visibility of where we stand with the health of the system. So with that, just a couple of minutes on track record, and I'll go to an example. So over 58 systems have been installed to date, electrical systems installed to date in carbonate, sandstone, single and multilateral applications. We've installed and inside of Openhole and in standalone screen type of completions. We've installed in oil-based mud and brine. So, there is a degree of robustness and a lot of experience generated from those installations and those production scenarios. 75% were installed in ERD applications, and we had the prototypes actually installed in 2012. The actual commercialization of the first electrical flow control valves was actually 2015, but we've had installations and those running since 2012 with 0 flow control valve electrical failures. We had some learnings in the early prototypes, and we had some learnings on the cleanup period, especially in oil-based mud, which we can discuss later if there is a particular question on. But none of those systems has failed electrically at all. So what that means is there is a very good, robust experience which has been generated with respect to electrical reliability. What that's allowed is access and reach. So as I mentioned before, 6 zones with 3 kilometers of contact and up to 14 kilometers of extent from measured depth from in this particular case, island drill sites. But those have allowed, a degree of capability from a management of the reservoir and multi-zone type of applications to improve the production performance. So what's at heart here, and I'm giving some real examples here to hopefully spur a little bit of interest in the last 15 minutes here with the petroleum engineering function. Those guys who actually have the responsibility to control the reservoir and produce the reservoir effectively and responsibly. So what we have with the ability to manipulate these control devices with very fine tuning is we have a highly sensitive control system. And on top of that, we have a highly sensitive measurement system. And what you see here on this chart is actually the measurements in an early cleanup phase of one of the wells, where you see one zone only producing, where what we were doing, we're actually choking this well back in 2% steps. So as I mentioned before, that's about 0 to 100% is the linear travel of the valve. And we're actually adjusting this. We're choking it back, decreasing the flow in 2% steps by linear. And you can see here, very small pressure changes here, which is relating to that zone, essentially, choking back, right? That's the response of the reservoir and the wellbore. That's a mini well test, if you really want to look at it. And you can see here in green, the response of the flow rate, the mass flow rate measured. In this case, it was all oil, so there's no water production on this zone, but you can see that these are very small steps in terms of production. In this particular case, 50 barrels a day. We have demonstrated sensitivity down to about 20 barrels a day in terms of being able to control that. So that's a pretty good thermostat, if you will, in terms of its control capability. The actuation time is also important. From full stroke, from fully open to fully closed, it's only a few minutes, 4 to 5 minutes. And what you see here is all this was done within half an hour. And this is done in full visibility. So if you're a production engineer and you're wanting to try to understand that zone, well, just adjust it by 2 or 3%. You're going to impact the production by 50 barrels a day on that zone. And you're going to learn a lot. You're going to learn about that zone, how it's performing. Did something good happen? Did I get an increase in rate? Did I get a decrease in rate? Did I get my productivity I expected? Am I starting to see water? This breeds confidence. And this is something which I think is vastly underrated, but oh so important, is the confidence of the petroleum and production engineer to utilize the tools that they have been supplied with. No point to have an intelligent completion if it's never used. So therefore, providing that confidence by that visibility is really, really important. And optimization of that wellbore can be done within 6 hours. In this particular case, 6 zones was optimized within 6 hours, as opposed to 6 days or 6 weeks or 6 months in some cases. And what this has enabled is this confidence, essentially, and the understanding of the reservoir that is driven, that between this period of time, this first 1 year of activity, which is the early sort of production phase, what you're seeing in blue here is the cumulated actuations of these devices in order to optimize. And you can see they come in waves. You see a series of optimizations in, let's say, the first 3 months. That's post cleanup. And then you see another one, optimization, a little bit later in the year, and then a bit more tuning at the end of the year. This is quite typical when you look at the different applications of those 58 systems deployed. It's quite typical. And you'll see 100, well, at least 10 anyway, 10 to 100 times more actuations than what you see in gray here, which is a conventional hydraulically actuated system, which tends to be only actuated when really necessary, but very rarely used for the characterization and understanding of the reservoir. Whereas when now we have electric systems that can be operated minimally, that means more actuation, more understanding, and more control ultimately of the reservoir. A cleanup example here. This is a 3-day cleanup. At the start of the cleanup, you see here this is actually 5 zone, or an example of 5 zones. You can see here that this top interval, which I'm highlighting here, is close to the heel. It's actually this interval here is dominating the production from day one. It's got the highest reservoir pressure. And you see the toe interval actually in this particular illustration is also producing, but the middle 3 intervals are not producing much. Now, because you have the visibility downhole in each of these, you're able to see this. You don't need to PLT, so you're able to see which zones are actually producing. And then in day 2, so next shift, they had went to sleep overnight, but came on shift in the morning. And what you can see is that what they did was they choked back the upper and the lower intervals. They actually reduced the choke on those ones selectively so that they could apply more drawdown to the middle zones. And 2 things you can see happen. The first is that you had a dominant second interval. This interval here, this was dominating the production under this drawdown because that's a high productive sand. But The middle, sorry, the two other ones in the middle here, these zone 3 and zone 4, these two started to produce. These are tighter intervals, less productivity, but you could demonstrate production and therefore recoverable reserves from these two zones, which is a significant value as well. And once you know that, now you can start to say, okay, now I know I'm getting production. I know my productivity from each of these zones. What can I do to optimize? And in this case, they set the optimal condition in day 3 of this cleanup. After only 2 days, 48 hours of cleanup, they set the optimal condition, which basically produced about 50% additional production than the previous days of production. So really impacting the early production, but also setting up the zones for the optimal production during the first year of operation. So a very important aspect is that early sort of characterization of each of the zones and demonstrating essentially what you want to do with them going forward. Another example here, which is actually doing very much the same thing, but is a 4-zone example where you had 2 producing phases. The first phase here, this is production rate on the vertical axis and time on the horizontal, but what we call balanced production. So the aim of this was to control for each foot of reservoir contact was to have an even amount of barrels per day producing. And with the exception of this lower zone here, this lower blue line, which you can see with highlighted with 300 barrels a day, basically this was being met with the other zones. The orange and the gray and the blue zones are here. I think it's zones 1, 2, and 3, the upper zones. So we're able to balance the production. And then after this shut-in period, which was more a characterization effort, what the aim was to see, can we optimize now for max production, given the max production through specifications through each of these particular tools or particular zones. And what you can see here is that for the upper 3 zones, they managed towards the end to get almost all of those to produce max. In this case, it was about 1,500 barrels a day, plus minus, for each of those zones. And they managed, because of the visibility of the tight zone, they managed to be able to more than double the production of that tight zone. So you see here, the 300 barrels a day was converted into 800 barrels a day from that tight interval. So what that managed to do is demonstrate the reserves from that particular interval, all without shutting in the well. We did not require this shut-in for the optimization. This shut-in was actually for the purposes of doing a build-up as part of the post-cleanup activities. But the ability to be able to do this while producing is highly valuable. And you can see here some of the transient tests for those well testers out there. This is actually a transient. In fact, these are build-ups, in fact, but they could be also multi-rate type of applications as well. What you see here is an example of a multi-rate test, which has the capability to be automated. So you see here at 1 zone, where we're actually manipulating these electrical devices. So 1 zone where we're choking back this well here, or this, sorry, not this well, we're choking back this zone. It's 1 zone of multiple zones, and then increasing. So we're doing a step rate test here, essentially. And for each of those step rates that you have the pressure and you have the flow rate. And of course, if you have pressure and flow rate, you can draw an IPR curve. What does that give you? It gives you your zone productivity and your reservoir pressure intersection, your P star, if you will. It also, if you do an analysis, you can do a rate normalized analysis, or you can do a pressure log-log derivative, conventional pressure log-log derivative type of assessment, in order to be able to extract skin and dynamic properties, maybe skin and KH from each of those zones as you're producing. So it's highly beneficial from a characterization perspective. One last key thing I'd like to leave with you before I show an example from one of the SPE publications is, I think it's also important to understand the ability for these additional measurements. And what we have here is a dielectric probe, essentially. So you see here it's what it's looking like. It's looking like a capacitance probe. So it's an electrical probe which measures capacitance of the fluid which is flowing past it. And what we've been able to use is we've been able to use the fluctuations of this capacitance. And you see here in red, this is real data from a paper referenced in the bottom there. What that shows is natural fluctuations caused by, in this case, horizontal well undulating, but there's fluctuations in the phase of fluids that is passing through this device. What that allows you to do is extract information about what is water dominant, what is oil dominating, and when it goes below a certain threshold value of the oil capacitance in this case, then what you can actually see is also indications of free gas. So what we've been using from this series of information is we've been converting this using a lot of the analytics capabilities to extract from the information of the capacitance and the downhole device, not only oil and water, but we've also been able to extract the signatures of gas. And you see here in red is the gas on this. This is a principal component analysis. Data scientists would know what this is, but it's showing essentially that information in a different visualization, which shows what is oil in green, what is water in red, and what is gas in gas in red and water in blue, excuse me. And what we can do with that information is we can pass that back into the algorithms for the flow rates. We can, number one, is correct the oil flow rate for the impact of the free gas, and we can actually extract the gas production rate as well. So what you end up with is you end up with moving from a two-phase meter, which is illustrated on this chart on the left, where essentially the original two-phase design of this tool was to measure water cut in green here at zero gas, and was impacting a little bit by small amounts of gas, but essentially enabling a two-phase meter, and now extracting much more three-phase information. The red represents still areas which are not measurable, or at least not readily measurable today with this particular combination of sensors downhole. But the green represents high reliability meteorological measurements of flow, both gas, water, and oil downhole, and the yellow represents indicative. So what this gives is a degree of certainty to the production engineer for managing both oil, water, and gas production in that case. So I'll close out on an example here, which is an example application. For those interested, the SPE references are placed again at the bottom. This is an ERD well, shallow seas, it's Caspian, and you can see here the arrows are highlighting the actual well 313 in this publication. And each of those red intervals here is one of 6 controlled intervals that is installed inside a standalone screen in this long reach green well trajectory that you can see here. This was quite notable in the fact that it was very shallow, so 1,500 meters TVD, but 63 or 6,400 meters measured depth. So quite a shallow long reach, but also if you can see and notice this well path is not that straight, right? There's a couple of 3-dimensional curves, right? Almost like a go down and turn to the right, as it were. So not that easy from an installation perspective. And with over 3.5 kilometers of contact from the top of the zone to the bottom of the zone. And if you look at it on an ERD plot here, this is where it is on the typical dog nose plot for those in drilling ERD wells. You can see here where it lands is quite extensive. It's almost into the extreme reservoir, extreme reach drilling envelope, which is really, one of very few wells that has been deployed. Now, when we look at it from a production perspective, so here we have 6 zones. Now, you're probably going to be a little bit confused by these, but I'll walk you through them. The 6 zones here, what you're seeing here on the right-hand side is you're seeing, where my mouse is, you're seeing plots of oil flow rate versus time for a 1-year production period, which is in the paper. And you're seeing here the different zones. There are 6 zones which are being measured here. And you can see 2 which are not producing very well and the others are producing. You also see the water measurements from each of those zones, and you can see 1 with an increase in water. And you're seeing on the bottom here is the gas flow rate. So this is coming from that algorithm that I just mentioned a couple of slides ago, is showing the free gas that is producing downhole in each of these zones. And immediately you can see that the blue one has almost no gas, or very, very little gas free production downhole, but the green one is producing a lot. And you may notice that the yellow one is producing a bit as well, at least in early stage anyway. And in the middle chart, you can see the pressure measurements for each of those zones. And I think you can immediately see that the yellow one starts with a higher pressure, but has a higher decline, as does the blue one. And 1 and 2, blue is zone 1 and and the yellow is zone 2. They depleted fast. Those are at the extent they're in a more fractured part of the interval, so they're dominated by the compartmentalization, etc. So there is a bit more depletion from those zones 1 and zones 2 from a reservoir pressure perspective. So just iterating what we can derive from this, and remember, this is all in one well. So we have essentially 6 zones that we're getting the information from. We're actually able to see what's dominant. So the intervals 1 and 4 are dominant in this case. The red and the blue are dominant. We have identified that we've got 2 zones. The toe intervals are depleting faster than the others. So that's a piece of information you would not have without running a PLT every few months, right? We're also showing that we have encroachment of water on this green interval, which is actually this interval here, number 3. And we're showing that the interval number 2, which is actually this yellow interval closest to the toe, initiates with the highest gas volume fraction. And in fact, it does have a lot more gas, or solution gas at that particular point. It's actually closer, or the gas cap is closer at that particular point in that particular part of the reservoir. Also can define that the zone 6, which is actually the heel section here, is ultimately the weakest interval, and ultimately not ultimately contributing much. So that could be for a number of reasons. It could be the reservoir depletion, or it could be the fact that it's tight or it's strained over time. It's a lower productivity interval. So very important pieces of information, and then I'll just illustrate for you differences in the way we've approached, or the way the operator approached the different parts of the operation with this capability. So we have the initial cleanup, noting that all the zones were open fully, and this was initially cleaned up. So this is the initial part of the well production scenario. And what you can see here is flow rate at the top again for all of the 6 zones. So this is liquid flow rate. It's not. I'm not extracting gas here, just the total mass flow rate. Capacitance, which I was mentioning earlier before, which is related to oil, water, and gas, and then the position. And what you can see here from the capacitance curves is from the flow rate curves we go first. You see this dominant interval, which in this case, in the early part of the production, is that middle one, the number 3, and the weakest interval was always this heel interval here in brown. But what you can also see is the trajectory of these capacitance. So this is in the early cleanup. So a high capacitance measurement is water or drilling fluid. And then as you produce, as that capacitance drops, you see at the point in which you start to produce pure oil. Pure oil is about this level here where this black line is, which is 0.7 picofarad. And then when the curve goes below that 0.7, that is really indicating free gas reduction downhole, either from crossing below the bubble point, or it could be a sign of gas coming from a gas cap from within the reservoir. But either way, it's giving you that indication of the gas. So it allows you to identify these things. It allows you to identify which are producing gas and which are producing and cleaning up first. And it allows us to be able to make decisions on what to choke. And you can see here that the heel sections were choked first in order to try to make sure that the toe intervals were producing effectively. And I think you can see here in yellow and blue, these are the flow rates of the toe intervals increasing towards the end, therefore designating that, look, they're actually doing a reasonable job at cleaning up and producing those toe intervals, which are important from the recovery perspective. I think for the purposes of time, I'm going to leave it there. I'm just going to conclude by skipping a couple of slides. So bear with me a second, because I didn't time this very well. But what I wanted to finalize on was what's next and why now. So what's next? I think I hope that I've got across an information of the ability to flexibly deploy electrical completions. They tend to be very high resolution completions at this stage, but they're not so high capacity. Each of these individual tools can handle about 3.5 to 5,000 barrels a day throughput maximum through these devices. So the next step is really to electrically actuate sleeve type devices, which allow you to get much more production through. So, upwards of 30,000 barrels a day potentially, which allows you to bring high capacity capabilities to those major offshore producers in whether it be a single trip or two trip type of styles like this. But if we look further, we also think about the sand face applications. There are opportunities there to simplify multi-zone sand control and provide the control, which is illustrated here in this animation, provide the control on the work string, so deploying as part of the sand face, deploying the intelligence and the control in each of the zones at the same time, and bringing the upper completion in and being able to connect up to it. So that can provide significant benefit to sand-prone producing reservoirs and simplifying the deployment there. And then finally, for some of the retrofit applications, so in existing wellbores, taking an existing wellbore, this could be a liner with an existing reservoir section. It could be already drained or partially drained where there's maybe some recoverables. Placing control devices in a stacked fashion, so running a control device, an electrical control device, stacked with this inductive coupler, milling out and drilling a lateral section. This could be a sidetrack into a higher oil saturation interval, stacking a junction control here, a second section to control this lateral, and potentially even doing it a third time. So you have a third one here. So the ability to be able to stack, because of electrics, be able to stack control devices could enable mature production, in-field extension, life extension of fields, etc. So the ability of the flexibility can help there. Couple of considerations to leave the team with. The first is that from the subsea perspective, there is a need to look at the interfaces, and therefore that usually requires a bit of investment in time, particularly on power provision. So I think I've mentioned that 96 watts should be sufficient to provide most downhole flow control valve applications, although more is always better, but 96 can get you quite a lot of flexibility. Additional electric devices, like for instance, safety valve, gas lift, chemical injection even, those obviously will increase the power if they're added to the flow control devices, so that will need to be taken into account. Wet tree electrical feed-throughs, very important from a architecture perspective, is to think about and provide for, as part of the tree capabilities, twisted pair provision. Otherwise, you're limited in what you can actually do and the reliability side. And then enhancing the feed-through reliabilities is topic of significant conversation and development work going on at the present time, because at the end of the day, it's all about the interfaces. If they don't work reliably, then of course the electrical downhole cannot be working reliably at the same level. And then finally, a consideration of health monitoring and digital aspects with respect to especially allowing access for the OEMs to health monitoring information. And what we mean by that is the visibility that electrical provides will enable enhanced reliability because of the use of the health monitoring capabilities of electrical systems. All those additional pieces of information that you can get from those downhole devices and visibility will help in terms of ensuring that their operation is done within the specification and for the longer life. I've got a couple of power simulations here. I don't propose to go over because of time, but what I wanted to leave you with is that this 96 watts in orange here is what is required ultimately at the tree level in order to be able to provide up to about 6 zones with a single connector, single inductive coupler connector. We've done this simulation for a 6-kilometer well case in terms of just getting some idea here. Simulations can be provided. So for those who are interested, of course, looking at this from an electrical engineer's perspective is important. We have simulation capabilities which can help to understand the power draw. But that's where I come to the last question. So when we talk about 96 watts, it sounds a lot maybe to the provision in a subsea tree system, but I've illustrated here for just a little bit of fun. Over here it's Thanksgiving last week, right? So every one of us had to put up our lights, within 3 days of Thanksgiving in order to be able to, meet the requirements of the neighborhood. But if you look at that tree, that's roughly 96 watts of LED light switches up there. That's a little bit less. Or that snowman is about the same thing, about 75 watts. And what we're actually doing today, and I'll come back to that bus, is the new Routemaster bus for London is apparently 12,000 kilograms, which is roughly 26,000 pounds, right? This could be lifted with 96 watts provision at surface with 2 of these zones, right? So when we talk about electrical completions, we are not talking about feeble type of devices. Anybody who's driven a Tesla will recognize they're pretty powerful beasts, right? But in a downhole scenario, we're talking about lifting a London bus with 2, with that snowman and that tree lights, essentially powering up for about 5 minutes to open those valves, right? So there is significant motor force downhole, and I think that can be utilized, very reliably. Why now? To finalize, 50 years of downhole electronics development and reliability. I think that goes a long way to demonstrating why the industry is ready. Care and attention to the robust electrical backbone, particularly with relation to health monitoring and capabilities on the telemetry, etc. Proven electric motor actuator track record, so almost 10 years now of deployed track records, up to 14 kilometers in wells, right? Utilization confidence is something which is really important. So production engineers who utilize these things, they do use the tools and they gain confidence. And that is an important aspect associated with the ability to, ability to deploy and the reason for deploying. It's of course digitally enabled. And today, let's be honest, there is also an industry pull from stranded reserves or the need to tie back to satellite facilities to, utilize the remaining life of those facilities that are already provided. Lifting cost and carbon footprint of developments are, of course, key today and will always be key for the future. But still today, there is an ability now to improve the responsibility or improve the ability to recover reserves responsibly. Facility utilization and even repurposing of existing facilities is enabled a bit more by electrification. And finally, generational demand. So I have sat in now 3 or 4 offices where petroleum engineers coming out of universities have been looking and utilizing these type of systems. And to have that visibility of the reservoir and the control capability at the fingertips of those guys changes their view on the petroleum industry. And I think that is something which has more meaning than any of the rest, is that for that next generation who's going to take this energy industry through to the next, next 10, 20, 30 years, that's really important, providing the tools that they gain the confidence on. They are the ones who are digitally connected. They're the ones who are drive-by-wire and accepting technology a lot better than, people like myself generation. So therefore, enabling those is really important. And I hope with this, I know I've gone over, Tim, I apologize, about 15 minutes more than I practiced. But I hope that this has given you a little bit of insights. And of course, I'm open up for questions. I realize I've gone well over the hour that I'd planned for it. So I hope that it's been interesting and open up for questions.
Yeah, very interesting indeed. Beautiful
Thanks.
bits of kit, aren't they? They really are amazing. Just astounding what you can do. There are a few questions that came out, 1 or 2 remarks rather than questions, but
Okay, I didn't see them.
This type of completion looks really expensive.
Yeah.
6 zones, how much would the well have to have in reserves? And he guesses 10 to 15 million barrels over 10 years.
So I wouldn't put it into the reserves bucket. I would put it into the productivity bucket, right?
Yeah.
And what we have assessed for different operators is systems, maybe not with 6 zones, but 6 zones would be, let's say an 8,000, 7,000 barrel a day type of producer. Something around 1,000 barrel a day producer is going to be a little bit low on the economic scale to, for additional recovery to pay off those type of devices effectively. But if you're in that, I would say anywhere north of 5,000 barrel a day is something to start considering. Of course, the more north you are, and then of course that 20, 30% extra will give you that recovery a bit better, right? So I hope that answered the question in reasonably.
Yeah. Well, just to come back, so what you're saying is if you're kind of what were the standard North Sea wells back in the 80s, 7,000 barrels per day, that kind of stuff. You're saying the optimization, the increment that you would expect to get by deploying a device like this would then easily pay for itself.
Easily in that case, Tim. Yeah. And as I say, if you're down to, we've done cases with 2 or 3 zones with down to 1,000 barrels a day, but typically land wells, so a little bit lower cost, obviously. But they struggle a bit to pay out if you're only getting an extra 20-30%, right?
Yeah.
But if you're in that sort of 5,000 plus barrel a day, then it's worth looking at for sure. And like with anything, you know, the first electric motor cars came out. The only reason people bought them is because, okay, they wanted to be responsible, but also they had the tax incentive. Of course, you know, now volumes are coming out. Of course, you know, those things are coming down in costs, and that, of course, will happen in this domain as well, right? Is the costs will go down for the hardware itself. I think the key thing though is reliability, right? Is to make sure that the things are working, and you know, hopefully, I've demonstrated that at least in the 8 to 10 years anyway.
Yeah, yeah. Vincent asks, which operator is the most advanced in using those electronic flow control valves?
So I can't really divulge names who are not published, obviously, but what I can say is the ones that have published is Saudi Aramco and Lukoil. So those are the ones that we have, or there are publications, and you can see them representing there. So they're not the only operators to have deployed, but I don't really want to divulge on this call. I can have obviously offline conversations with that, but certainly Lukoil and Saudi Aramco are the ones that are most advanced with these things. I think it's important to mention that there is recent activity in offshore North Sea, which would spur some future interest. I think, you know, North Sea was the birthplace of intelligent wells, and I think, you know, today it's also showing that it's starting to get interested in electrical, and therefore, you know, there is a deployment in the North Sea, but I can't say more on a public space at this stage, Tim. So yeah, sorry, Anton.
I did notice that the whole of Russia was coloured in already deployed.
Yeah. From east to west, Tim. Yeah.
Because most of the stuff is quite low productivity. I mean, I suppose the stuff off Sakhalin is pretty high, and some of the stuff in the Arctic is. Yeah,
I mean, I think the key thing here is a couple of drivers, right? The published one is Caspian, right? And you'll see it right from the SPE, right? But rationale is they have platform, right? And they have an extensive field, right? So they need to have these long reach wells to extend to the field, and they have ice forming in the wintertime. So the structures, you know, the cost of structures is high, right? That same could be deployed, or same principle can be deployed in the eastern side of Russia as well, Arctic type of stuff, right? So by that you can probably deduce where.
No, I got it. Yeah. Okay. Let's see if any more questions came out. No. Can we retrieve the lower completion? That's an interesting question. That's
a very valid question. So there are the short answer is yes, if you plan to have it retrievable. So I would say if you place a lower completion inside of a standalone screen or slotted liner, and you have retrievable packers, you can retrieve them. It is possible. It's of course a mess, but it is possible. If you are deploying these devices in an open hole environment, then clearly the ability to pull those is a lot more complicated. But if you place the lower completion as part of an inner string, like I illustrated here inside of stand screen, yeah, you can provide them with the ability to pull afterwards if really needed. Yeah.
Okay. Are there any other questions that people want to raise? I mean, we've got a couple more. Bashir, yeah. Okay. How robust are the simulated models for optimizing production? How robust? How accurate?
Yeah, very good, Bashir. So look, I don't know if I have a good answer for you know, how robust are they? What I can say is that the team, our teams in Abingdon, probably familiar with those guys. They've done a lot of work on the reservoir simulation side. So there is a lot of optimization under uncertainty models which have been used. Our colleagues in the research centers and in Abingdon have been doing a lot of that. That's number one. Number two is that because you are getting the information from each of the zones, so you're getting production rate, you're getting water cut gas, you're getting pressures, and of course, you know, flows and all of this, right? Because you're getting that during the time, then your ability to be able to update the model, as long as you have the fidelity in the model, the update the model with the characterization as it occurs is higher. Now, that requires a lot faster iterations on the simulated sensitivities and history matching, right? Which the newer breed of simulation tools, I know that I think it's Intersect is one of them that enables a higher speed of processing, but is allowing today to do. So I would say maybe it's not the model in itself as much as the ability for the model to do fast iterations, but then using and inputting in the information from each of the zone pieces of information, right, to update the model. And I think that once you update, of course, then once your history capture, of course, you've got a much better simulation certainty. And then what you can do is utilize the capability then to do what if scenarios with much more confidence. And I know it's a long way around of saying it, Bashir, but I think that it's a bit of everything. But key in there is simulator speed and the ability to update with actual measurements over time, not just sensitivities on your first well test, right? Now you're getting it over time. I mean, you're getting it every second if you want to do it every second. But that's really my answer. I hope it answered the question.
Well, it prompts another one for me, which is that, I mean, you did talk about principal component analysis, demonstrating that data size have got in there. But the broader point is that if you have so much data being generated from this these devices, then you are in the data science, data handling regime, and you really ought to be able to use that to forecast the exact optimum number of screw threads that you put in each of those flow control valves and all the other things. So that's just a module you put on the back, isn't it? So rather than doing maybe a pure physics simulation of what's going on, you have a hybrid physics data science module, something like that.
Yeah, Tim, I think that's a highly valid point. So that I think there's the physical model, of course, which you have from the simulation capabilities, but there's also the ability to do what if scenarios and learn from the patterns of activity. And what we have applied because we have access to some of the health and some of the physics information from these producing wells, right, is we've been able to use that data science to be able to extract an additional phase of measurement, in this case the gas, right? So we're able to do that. That's a module you can add. Now, when it comes to the production information, they tend to be maintained within the host, in this case the host operator, and for sure there is an ability to utilize those. I'm sure those operators are actually utilizing that at this present time, but obviously without the data access, then that's going to be difficult for a service co to be able to deploy that machine learning at that stage, right? So for sure, I think it is definitely an area of interest, and I'm sure there is going to be some work on that coming to light soon enough.
Yeah, it's exciting stuff.
Yeah.
Does anybody else want to make any final remarks? Anyone else? So I think we're probably done. Hey, Steve, well, that's fantastic. And thanks, Tom, as well. You're still there. Nice to hear from you. I suppose you should have asked some piercing question about how you could apply this technology to geothermal, but I think probably the hot water would have to flow very fast to make it economically viable.
I think there will be a challenge there, I think, Tim and Tom.
Okay, well, Stephen, thank you so much indeed. Fantastic, very, very interesting, and I thought the graphics were superb because I'm not naturally skilled in visualizing these things, but I thought the way that those visualizations were excellent, so I grasped it all pretty quickly. Thank you.
But thanks, Tim, and thanks for the invite, and apologies for my tardiness on getting back to you in